guys.
All right, let's get started. Okay, so today you picked up 2 handouts. We're starting the next unit. Let me have your attention, please. Look up front. Time to focus. Okay. All right, so we're going to talk today about some special segments that are in triangles and some relationships that happen there. Okay, so starting out with, we have a couple of terms we're going to look at. And the first one is the perpendicular bisector. Okay, so when you look at this picture that you see right here, we have dealt with many perpendicular things. Lines that meet at right angles. Okay, we've dealt with bisectors, which is something that cuts a segment into 2 congruent segments. But together they are called a perpendicular bisector. Okay, so in this picture, CP is a perpendicular bisector of the segment AB. It is that because it's got a right angle and you have 2 congruent pieces. Okay? Now, what we're going to talk about is there are some special relationships that come up in our theorems, okay? In our theorems, they use this word equidistance. So you need to understand the meaning of this word because you probably never heard it before. Equidistant basically just means the same distance from, okay? So they are equidistant from something. They are the same distance from something. Okay, so let's take a look at the first theorem, the perpendicular bisector theorem. Okay. Now, one thing we're going to work on is being able to distinguish between these 2 theorems. One is a regular theorem, one is the converse of the other theorem. Okay? So, starting out, the perpendicular bisector theorem. It says, in a plane, if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay, so I'm going to ask you for some pieces, and I want to hear from everybody, okay? So, in that picture that you see, what is the point that lies on the perpendicular bisector?
C.
C. Is that clear? Okay, so what is the perpendicular bisector? Say that one more time. CP. CP is a perpendicular bisector of what?
AB.
AB. Is everybody clear on that? Okay. So according to this theorem, it says that C will be the same distance away from the endpoints of the segment. What are those endpoints?
A and B.
A and B. Okay. So if this is a perpendicular bisector, this point that's on the perpendicular bisector should be the same distance from the endpoints of the segment, okay? So they give it to you right here, CA equals CB, okay? So basically you have to recognize you have a perpendicular bisector and think about that point. It should be the same distance from the endpoints. So what that means is I could put a point anywhere on there and it would be the same distance, yes? So these lengths are congruent only if it's on the perpendicular bisector, okay? And I could draw one way up here and these lengths would be congruent to those endpoints. Does that make sense? Okay, that is called the perpendicular bisector. If a point lies on the perpendicular bisector, it's equidistant from the endpoints. Then the converse. The converse of that theorem is that in a plane, if a point is the same distance from the endpoints of the segment, then it lies on the perpendicular bisector of the segment. Okay, so now they have everything labeled in this drawing. But if you notice here, you've got this point D that's not really on the line in the drawing. However, it would continue through it, right? Okay, so according to the theorem, these pieces being congruent tells us that it's on the perpendicular bisector. Now, I'm gonna give you some examples of this, and we're gonna try to recognize which theorem we're using. Do you have questions? Yeah. Okay, all right, so let's look at some examples. Okay. Is there enough information in the diagram to conclude that W lies on the perpendicular bisector of XY?
No,
Why not?
because we don't know that they're perpendicular, that WC is perpendicular to X, Y.
Good, so not perpendicular, okay? Clear enough?
Yeah.
All right, moving on. All right. Using the perpendicular bisector theorem, I want to find the AC in this drawing,
It's 7.2.
7.2. Now, I want you to tell me, am I using the perpendicular bisector theorem, or am I using the converse?
Using
Perpendicular bisector theorem.
And you know that because you started with the perpendicular bisector, and it told us that the point A was the equidistant from the endpoints, right? Okay, so it did not make you explain it here, but we're gonna explain some in a few minutes, okay? So we're trying to do that as we go. Okay, so let's go on to this drawing. What am I looking for?
22. KM.
Oh, KM. Okay, am I using, which one am I, which
The
theorem?
converse of the perpendicular line.
It's the
Perpendicular
converse?
Yes,
Okay, how do you know it's the converse?
because we're taking JN and JK, and the congruence, that means it's the thing.
Okay, so who can explain that with the theorem, using the wording of the theorem? What would you say?
If JK is equal to JM, then point.
Then point J lies in the bisector of
Could you not?
Almost, okay, together, I think y'all got that.
Yeah.
If JK is congruent to JM, then J is a point. Sam, stop. Stop talking.
I wasn't talking, I was,
Okay, no, no.
Chatting.
Okay, so J is on the perpendicular bisector of the segment, okay? Which tells us that you have a perpendicular bisector because these pieces were congruent, right? Okay, so this is the converse, okay? The answer is 22, okay? Moving on. We'll move on.
How do you know? Oh, wait, never mind.
Okay, that was the converse there. Okay, now we're gonna look at one more idea here. Okay, this one is about an angle bisector. Okay, so you know that the angle bisector is a ray that divides an angle into two congruent angles. Okay, so it should be pretty clear to you in this diagram that since these angles are congruent here, you have an angle bisector, right?
What did you draw?
I don't know what I did there.
What are you doing? I'm confused.
I made a mistake, sorry.
Golly.
Patience, sorry. Because these are marked congruent, we know we have an angle bisector,
Yes.
right? Okay, now according to the angle bisector theorem, if you have an angle bisector, a point lies on the angle bisector. What point lies on the angle bisector? D. D is a point that lies on the angle bisector. Does that make sense? Okay, then it is equidistant from the two sides of the angle. Now here's something you need to remember. When you talk about the distance from somewhere to somewhere, when I say the distance, find my distance from here to that wall, I'm not gonna go that way. I'm gonna go straight to it, perpendicular, right? When I do the distance to that wall, I'm gonna go perpendicular to it, right? So that's understood when we're talking about equidistant from something, okay? Which is implying straight perpendiculars, right? Does that make sense? So this is saying if you got a point on the angle bisector, it is going to be the same distance to the sides of the angles. So that's implying the right angles, right? So the converse will also be true. And we're gonna look at this and try to determine, are we doing the regular angle bisector theorem or the converse in just a minute. Okay, so if a point is in the interior of an angle, okay, what point is in the interior of an angle?
A, B.
D. A is the vertex, so it can't be A. D is in the opening, right? In the interior. And is equidistant from the two sides of the angle. What lengths show that it's equidistant? What lengths?
B and C.
BD and CD. And you know that because of the marks, right? Everybody good? So if these marks show that D is equidistant from the sides of this angle BAC, then that is enough to tell us that D lies on the angle bisector. So from knowing this, we're now gonna know these angles are congruent, right? That makes sense? That's what that's showing you.
Wait, could you explain that one more time, please?
Okay, so because D is a point that is the same distance from AB, the side, the ray, and CD, because those are marked congruent, we now know that D lies on the angle bisector, which tells us these angles would be congruent. Does that make sense? So that is the converse. In other words, you get the angle bisector because you know those lengths are equal, right?
If it doesn't have the congruence marks, does that mean that it's not the converse theorem?
It would mean that we don't know it, right?
Oh, okay.
So it could be.
I don't know that it's always gonna be marked. I can't answer that, because you never know what you're running
Is
into.
for the angle. The normal one, we know the interior angle, right? But the converse, we don't know. So if we know it, it's not the converse. If we don't know it, it's the converse.
I think that's what he was asking, isn't it?
Yeah.
Okay, so let's look at a few examples, okay? And then we're gonna have to quote some of these in a moment, okay? So the first example, is there enough information in the diagram to conclude that point D is on the bisector of angle ABC?
Yes.
Yes. Okay, so yes. Explain. How would you explain?
The converse angle, the converse of the angle bisector theorem.
The converse of the angle bisector theorem. Now, you could say that, but you also need to know what it says, right?
Yes.
Okay. So if I were to ask you to quote it, could you quote it
Vaguely.
vaguely? At this point, that's okay, because you just learned it, right? So it says, if a point is equidistant from the sides of the angle, then it lies on the angle bisector, right? That's the general idea. If the point is the same distance from the sides of the angle, it lies on the angle bisector. What conclusion could be drawn now from that? What that angle ABD is congruent to DBC, right? That's what's implied? Okay. All right, next. Find the
54.
measures. These should be pretty quick.
54.
Oh, you're just so quick. Okay, so slow down a minute. RPS. Okay. Now, it's obvious here, this is 54. But I wanna know why, other than adding them. How do you know those are congruent?
Converse angle bisector.
Is this a converse too?
No.
Is it?
No. Yes.
Is it?
Yes.
This is a converse.
Yes.
Okay, we got your answer.
It's not converse. It's not converse.
Did you start with the angle bisector being known?
No.
No.
Ah.
The 27s are what make it an angle bisector, right? So this is a converse. So this is the converse of the angle bisector theorem. In other words, if the point is the same distance from the two sides, then it's on the angle bisector, okay? It didn't ask you for that, but this is a converse, okay? What about this one?
33.
That's what I think.
Because 7x minus 9 equals 5x plus 3.
Okay, so you just set them equal.
And this one.
Now,
is-
all right, Brian, don't tell me, okay? You've been very involved. Let's get some other people to be involved.
Solve
All right, so obviously you solved. Y'all did the algebra part, that's the easy part. Now tell me, what do you know, why? What's the reason?
Because the angle bisector theorem,
Okay, is it regular?
yes.
It's regular, because we started with knowing the angle bisector. Okay, so this is the regular angle bisector theorem. If we have an angle bisector, a point on the angle bisector is the same distance away from the sides of the angle, right?
So the answer would be 33.
So the answer here is GE, we got 6, and then we had to plug back in, I didn't finish it up. So 42 minus 9 is 33? Yes?
Wait,
Yes,
Sean?
yes.
And this was angle bisector theorem, yes, sir?
Remember the example for the 6.2 theorem?
We haven't been to 6.2.
Bless you.
Yes, it's right here on the front page.
6.1?
6.2, I'm talking about 6.2.
Back up here, what about it?
So what's the angle bisector? Would it be CP or?
Okay, this is a different situation. We were dealing with segment bisectors here,
Right, I'm just confused, like, what is the segment bisector? Like,
What is the actual thing?
yeah, what separates?
This is a segment bisector, CP.
Does it
But,
say
but we're
where-
not working on that right now, right?
Right, I was just wondering.
So that's all you're asking?
Mhm.
Does that make sense?
It's a line bisector with a segment. The segment is.
Okay, so moving on. Now we're gonna have to answer and explain a little bit. Here we go. All right. Tell whether the information in the figure allows you to conclude that P lies on the perpendicular bisector of RS. Explain your reasoning. Try number 1 and 2, but don't say your answer yet. So once again, you're trying to find out, is P on the perpendicular bisector? That's the question. So on number 1,
Yes.
it is yes.
Because of the,
Okay, Blake, why?
I forgot to write that into
Okay, is it actually a theorem?
Yes, it's a theorem.
converse of the perpendicular bisector theorem.
Well, I guess it could be that, but isn't this just clearly marked as a perpendicular bisector? So this one would just
definition
be,
of perpendicular bisector.
this is just definition of perpendicular bisector. It has the two bisected pieces, and it's meeting it at a right angle. Okay, so I would say this is just a definition. Does that make sense?
Do we not have to use the theorems?
No, not that one.
Not if you had to on this, because all they said was, do you have a perpendicular bisector, right? So this is by definition. Okay, look over at this one.
No.
Yes.
That is definitely not by definition, right? Because these are not marked congruent, right? Okay, so the question becomes, does it satisfy one of the theorems? And if it does, is it the converse or the regular perpendicular
It
bisector?
doesn't satisfy me.
It
Yes,
does.
it does.
Hold on.
It does, but like it's.
Okay, we have
It doesn't satisfy.
We have a point that's equidistant from the endpoints.
It satisfies the converse.
What is that point that's equidistant from the? T is actually on the perpendicular bisector because it's equidistant from the endpoints.
So is
But if T was, then that means P could be also, because they are obviously collinear, right? So it does satisfy the converse. But the segments aren't drawn.
No,
So you
the
can use
segment,
converse.
the RS is a segment. RS is a segment, because it doesn't have arrows pointing.
No, but I'm talking about these segments.
The same one for RP.
But
I
you're
thought
not,
it was just regular.
no, but you're not trying to find if,
perpendicular bisector.
you're not trying to find, you don't need those segments. You're just trying to find if P is on the line, it doesn't, the point doesn't have to be P.
Yeah, she already said that.
No, we're trying to decide if P is the same distance from the endpoints.
Oh.
Because if this is the same distance from here to here, then we know these are equal according to the
I thought it was
contour.
just asking to see if P is
Well,
just
It's on the
Well, if-
perpendicular bisector.
But if it isn't a perpendicular bisector,
It is
doesn't.
though.
It is.
It is.
That's questionable.
It has to
Could
be.
you use Converse?
Well-
Yes, it's converse.
It's Converse.
Yeah.
It has to be because it's collinear with point T. It's on UT.
It gives you RT.
Yeah, T lies on the perpendicular bisector, P line lies on
UT
the
is
same
I want to
line.
say yes because of the converse, but it's not your typical case, is it?
It is. Is it
Yeah,
not?
it's
It
just
is not your typical.
TU is the
Just
perpendicular bisector.
U-
and P
UT.
lines on UT.
UT.
Okay, so if this makes this a perpendicular bisector,
Yes,
And P lies.
then we could say P lies on
it
it.
does.
It does.
So are we using the converse or the
Yes.
regular?
Yeah, we're using
The
the
Converse.
Converse.
We're using
Because the
regular.
only thing we need to prove is
Converse.
T makes it, T makes
Okay,
it
so
true.
let me say this, let me ask a couple questions. Because T is equal distance from R and S, what's congruent?
RS.
What pieces are congruent?
RU and US.
Okay, so that is the converse, right?
Yes.
So because T lies on there, RU is congruent to US, correct?
Yes,
Okay, that's the converse, right?
right.
Because it was on the, it was equidistant, right? Okay, so now that we know these are congruent,
Yes.
then we can say this point here lies on the perpendicular bisector. What are we using?
The Converse.
We're actually using the regular perpendicular.
Because we just need to find if UT is a perpendicular bisector of the triangle.
Okay.
We don't have to find that P is equal this one.
You do have to find out
Where-
about P.
It just asks
Oh,
if
The
P lies on the
question
perpendicular
was
bisector.
about P. The answer here would be, because of the converse, we know we have a perpendicular bisector.
So,
And then we could say it is on, I guess you could look at that either way now that I think about it. So I would probably take both answers, but in a realm of thinking.
how could you prove that it without Converse?
Well, you would have to use the converse and then think about that you have a perpendicular bisector.
And P
Before
lies
you
on-
said yes, is what I'm saying. Okay? So you're really just using, I should look that up and see what the blue is. Okay? But I believe it's probably, I think that's a good explanation. Let's move on. Let's don't get hung up on it. Let's go to the next one. I'll check on that. Find the indicated measures. AD.
20.
Okay, is this the converse or is it,
Converse.
this is the converse or is it?
No, it's
No,
regular.
no, it's
It's
normal.
regular.
It's normal.
Okay,
Oh,
so
you said you just said converse, so-
explain in words without saying the word converse or regular.
For which one?
Okay, so,
A, B, and BC are congruent.
so AD is 20. Now tell me why, explain in words.
Because angle ABD is perpendicular, and it bisects AB and BC, because they're congruent.
So it's bisecting.
Or AC, yeah, bisects AC. And then,
Okay, somebody else try. James, what do you say?
Because angle or line BD is perpendicular to AC and also bisects AC, then it is
Keep going, you're good.
equal distance from point A and point C.
Excellent, okay. Which one was that? Was that regular?
yes.
That was
Perpendicular bisector?
That would be
or
regular.
That would be regular. Because you're saying if D is on the perpendicular bisector, then D is equidistant from the endpoint. Yes?
Yeah.
Okay, y'all learn how to write that out. If, I'll write it with you, D is on the perpendicular bisector of AC, then it is equidistant or the same distance from A and C. Also known as the perpendicular bisector theorem, correct?
Yes.
Okay. All right, number 4.
17.
You set them equal and then you plug back in. So without that,
17.
okay, I wanna know, is this the same reason as number 3?
Yes.
Or is it a different reason?
It's the same.
It's,
It's the same.
How many of you think it's the same?
No, it's different.
I got
We already know that both sides are parallel, I mean, that both HG. and
Okay,
G-
raise your hand if you think it's the same as number 3 for the reason. Raise your hand if you think it's different. Okay, we've got a little bit of both, okay? The question becomes, do you know that you have a perpendicular bisector?
Yes.
yes, you do.
Yes. So the point G is the same distance from the endpoints. This is the regular perpendicular bisector
You
theorem.
said it was the opposite.
Oh,
So it is the same as number 3, okay? So perpendicular bisector theorem. And I'm not gonna do the algebra, the hard part here is
It's 17.
figuring out what you got.
It's 17.
it's 17.
It's 17.
Oh, the answer's 17?
Yes.
Leanne? Yes? Yes. All right, let's move on. Now, we've talked about that. Time to change gears. We're gonna talk about angle bisectors. Tell whether the information in the figure allows you to conclude that EP bisects angle DEF. All right, don't yell it out. Everybody look at it, make a decision on 5 and 6.
What are we doing? 3 and 6? 5 and 6?
5 and 6.
5 and 6.
Okay, one of these is no. Which one?
6.
6 is no. Everybody agree? 5 is yes, and then we have to decide why.
Because of the converse of the angle bisector.
Very good. We do not know in the beginning we have an angle bisector. We are determining it because P is equidistant from the sides, right? Okay, so this is the converse of angle bisector theorem. Okay? All right, number 7 and 8.
No.
Find the indicated measure. Okay, what's PQ?
14.
14. What's the reason?
Angle bisector theorem.
This is the angle bisector theorem because you started with the angle bisector, right? And because you had a point Q on the angle bisector, you know it's equidistant from the sides, right? Okay? Angle bisector theorem. All right, number 8.
38.
Okay, your answer comes up to 38. Do y'all agree?
76.
Okay, so what's 38?
38 's DGE.
So that's one
It's
answer.
asking for DGS.
Okay, so basically
Oh.
you're setting these
I see that.
equal
Yep.
and solving for x, right?
Yeah.
Subtract 3x, you get 2x. Add 12, you get 20. X is 10. This would be the work required. Plug in 3 times 10 would give us 38 right here, right?
Yeah.
Multiply.
And double it, and your answer is
76.
76. Now explain.
Converse.
Converse of the base angle, or angles bisector theorem.
It is converse. Very good. You guys are doing really well. So if it's equidistant, if the point E is equidistant from the side, then the two angles are congruent, making an angle bisector,
So
right?
wait, the answer's 76, right?
Yes.
Yes. Okay, now just a couple of things on your homework and such, okay? So I have for you, we have about 10 minutes, okay? We're gonna talk a little bit about square roots, okay? What is it?
What? Sorry, you go
Alright,
You.
can I go to the restroom?
Yes, what is it, Jason?
So for number 6, the reason for it was because of
The converse,
the converse.
because it was equidistant from the side first, that made it have an angle bisector.
Cause for Converse, you don't know the angle, the big angle,
And
and you don't know the big angle here.
and why did we say no for number 6? Like,
Because you don't know that, because you have to either know the big angle, which is, big angle E, you have to either know that, or you have to know the segment DP and FP on congruent.
Okay, so all we had in that picture number 6 was right angle. That's not
Which isn't enough to-
Something's gotta be congruent, okay? All right, now, on the assignments. Multiplying square roots you picked up today. This will be due on Tuesday of next week, so this can be an ongoing piece of work, okay? Again, we're trying to get you prepared for when we start doing area, so you're good at working with these numbers, okay? Now, so I'm gonna run through just a couple of these the last part of class, and then you have an assignment today that is the odd problems, 1 through 21 odd, and 27 and 28 on the board from page 296. That you should have done by tomorrow, so that we can move forward with our new stuff, okay? So you've got 2 assignments, one is due
21
next
off.
Tuesday.
Nate, 1 through 21 on, 27 to 28.
Yes,
Page 296.
yes.
Assignment number 16.
Yes, all right. Now, I do need to show you how to do a few things with this multiplying radicals, okay? So first question, Sam, you ready?
Yes.
are we doing all of these?
All right, we're gonna do the ones I circled, and then you're gonna do the rest of them, okay? So number 1, the square root of 5 times the square root of 5. Sam, what would you say?
Square root of 5, wait. Square root of 5 and square root of 5. What did I say?
What would you say? Equals? What? 5. You got it. Did you know it? Did somebody have to tell me?
Yes.
Okay, so basically you can multiply underneath the radicals, and then the square root of 25 is 5. So if you multiply 2 square roots together with the same number, you get what's underneath, okay? In other words, if I gave you the square root of 10 times the square root of 10, that's just 10. Yes?
Yeah.
Okay, you're gonna run into some of that as you work. Number 4, okay, I'm just choosing a few of these. If you follow that same pattern, this would be the square root of what?
200.
200.
200.
And.
Now, sometimes you can break that down, right?
Square root 2.
So, Nate, what would I write it as?
Well, 200 can be broken down into 102, and then 100 can be taken out as 10, and so it's 10 times the square root of 2.
Okay, everybody okay with that?
Wait,
Okay.
why couldn't we like make it to where we simplify 20 so it would be
You can do it
Because
that
that's
way.
4 rings.
so
Okay.
like it'd be 2 on
All
the
right,
outside?
let's look at that method, because it also works. You could have done this as 4 times 5 times the square root of 2 times 5, right?
Yeah.
The square root of 4 would be 2. Then you still have a 5 and a 5, right?
Yeah.
The square root of 5 times 5 would be 2 times 5 times the square root of 2. At some point, you're gonna put them in the same square root.
Oh.
Does that make sense?
That makes sense. Yes, ma'am.
So if the numbers are smaller, you might want to do what he was just saying. I'm sorry, I said that wrong. If the numbers come out to be a really large number that's unhappy, not a happy big number, okay? Then you break it, if you break it down smaller, it might be easier, okay? Another way to say that. Number 6. Everybody do number 6.
Okay.
Okay, so we start with 60. Then what?
2 square root of 2.
So 4 times
4 times 20. Right? No,
No.
15.
4 times 15, right?
Yeah.
or 4 times 5 times 3, right?
Yep.
And 5 and 3 are prime, so it becomes 2 square root 15.
Wait, couldn't we simplify it even further?
No, 15 is 5
yeah,
times
yeah.
3, okay?
Silly bomb.
Write your answer for number 10.
Ew. 10?
Number 10.
Oh, I got it.
Okay, now I choose this one because this one has a number on the outside where the others that we did not, okay? If they're on the outside, you don't multiply with the ones on the inside, okay? So, on this one, all right, somebody besides Nate, you did the last one, so hold on. Jason, you do this one, do this one.
So first you multiply the outside numbers, so -2 times 1, which is -2, and then you multiply the square roots, so it would be square root 10, and that's your answer.
And that's your answer, because you can't break down the square root of 10. But if you could, you pull it out, and whatever you took out, you multiply by that 2 on there, right? So you've done a little bit of this, okay? All right, moving on. Number 14. What property applies? What property?
Distributive.
Did everybody distribute this?
I haven't started.
I'm giving you a second. Go ahead and distribute this square root of 6.
Oh,
You should have 2 different radicals added after you've done that. You should be writing. You should be writing.
Do you still get the same thing if you don't distribute?
okay, I got it.
What did you say?
Will you get the same thing if you don't distribute?
I don't know how you can do
Technically,
this
yes.
without distributing.
Technically, if you
Hold on,
put the bill
hold
on,
on, hold on,
it's the same thing.
hold on. So when you distribute, did everybody get this?
Yeah.
Everybody got that? That's your first step, right? Okay, now we break both of those down, right?
Square root 30.
So this would be, now
Square root.
you can't add under the radicals. They are not like radicals. Remember how we only added like radicals? Like square root of 2 plus square root of 2, you can't add underneath. But you simplify each, okay? All right, Blake, square root of 12, what is it?
Square root of 12. It would be 2 square root 3.
So 4 times 3, 2 square root of 3. Good. Tell me square root of 18, Blake.
Square root of 18. It would be 9 times 2, which is
9 times 2, so 3 square root of 2. Good. Can you add these?
No.
No. This will be your answer. This would
Do
be,
you not multiply from the outside in? How we did on the last one?
what do you mean? Well, we did multiply the root 6's, right? Root 6 times root 2 and got root 12. That was our first step. That make sense?
I have a question.
Yes?
Like number 9 and number 12. We didn't do them, but, so, could I just, would it just be like, for 9?
All right, let's don't give the answer away, but I will tell you that your answer is an integer,
Is it,
okay? That means you will not have a square root in your answer. It will be like 45 or something like that. Okay?
okay, so,
All right, so we gotta stop right there. I'm gonna move back to the first screen, okay? Yes, that's right.
that's what, yes.
All right, now I will put the answers on the board randomly for you tomorrow. Y'all have a good afternoon. Oh, it's still recording.
It's like for 8 to get
Long recording.